In this video, we're going to be looking at topic 2D, the reactivity series, as part of the IGCSE chemistry course from Edexcel, and we're going to be focusing on the single science outcomes. So for single science, you need to know how metals can be arranged in a reactivity series based on their reactions with water and with acid. You also need to know the reactivity of specific metals, know the conditions under which iron rusts, and understand how the rusting of iron can be prevented by things like barrier methods and galvanizing. So what is the reactivity series? Well, the reactivity series is a list of metals or a series of metals that are in order of reactivity from highest to lowest. And you can see that we have a picture of the key metals here. We're going from potassium all the way down to gold. Now, there are some other metals that are not on this list that you may come across, but you'll be able to work out where they would fit in by using predictions about what you already know about the reactivity series and where you think they will fit. So metals that are at the top of the series are the most reactive. So they are going to react with water, with oxygen, and with acid. So they tend to be your alkali metals, potassium, sodium, and lithium. Metals that are at the bottom of the series, they tend to be the least reactive. So they're not going to react with things like water, oxygen, or acid. And a very good example of this is gold. We use gold to make things like jewellery. So of course, if we had a ring or a watch or a necklace that was made of gold, we would not want it reacting with oxygen or with water, or else it could cause a chemical reaction that could actually cause some damage to us. So let's look at the specific reactions of metals with water. So any metal that is above hydrogen on the reactivity series, so if I just go back here, so any metal from here upwards, so from potassium down to iron, are going to react with water or steam to produce hydrogen. If it's a metal and cold water, we're going to form the metal hydroxide and hydrogen. If it is a metal and steam, then we're going to form the metal oxide. And as you go down the reactivity series, the reactions become less vigorous, and that's because the metals at the bottom have a low reactivity. Anything that is below hydrogen on the reactivity series is not going to react with water. Again, any metals above hydrogen can react with acid, and they will form a salt plus hydrogen. So this is an example of a neutralization reaction as well, because we're making a salt, and we have covered this in topic 2F. So if we have a metal plus hydrochloric acid, we're going to form a metal chloride and hydrogen. If it is a metal and sulfuric acid, you'll form a metal sulfate. And again, as you go down the group, the reactions become less vigorous, and metals like zinc and iron need heat in order to react with acid. So the closer you get to hydrogen, the more energy you actually need to put in order for the reaction to happen. So our more reactive metals will react when it is cold and we don't need any heat. But as we go down and they become less reactive, we have to have heat in order to kickstart the reaction. And anything below hydrogen is not going to react with an acid. So that would be gold, silver, or platinum, or even copper. So we can make predictions using the reactivity series based on how it is going to react, or we can even figure out how it's going to react based on where it is in the series. So what we would do is we would do 3 steps. First of all, we would add a small piece of the metal to cold water. If it reacts fast, then we know that it is a reactive metal, and it should be above magnesium on the reactivity series. So it's going to be near the top. If there is no reaction with water, what we would do is we would then move and we would go to adding an acid. And if it reacts, there is going to be the metal being placed on the reactivity series between magnesium and hydrogen. If there is no reaction with either, then the reactivity of the metal is quite low, so the metal is going to be below hydrogen on the reactivity series. Now, you may not be able to say exactly where it is, but you can at least give a rough area of top, middle, or bottom. So now let's look at the rusting of iron. Iron rusts in the presence of oxygen and water. Okay, so iron, being a metal, is going to form a compound known as iron oxide, which is sometimes known as rust, when it is in the presence of oxygen and water. And this happens when our iron 3 ions are oxidized. And you don't need to know too much about oxidation in terms of what it is at single science. This just means that it loses electrons to become an ion. And the chemical formula for rust is Fe2O3 with a specific number of waters, and it is known as hydrated iron oxide. Now, please be aware when you're talking about rusting, you can only refer to iron as a substance that will rust, because this iron oxide is also known as rust. So iron 3 oxide is rust. No other molecule or no other metal can form this compound. So if we're talking about the reaction of any other metal with water or with oxygen to form this metal oxide, then we call it corrosion. Okay, so please make sure that we understand that those are not interchangeable words. Rusting is a form of corrosion, but not all corrosion is rusting. So it's important to prevent the rusting of iron, because any rust that builds up can damage the structure of any objects, or it can even break them. And this can cause major accidents if it was something like a bridge or a building structure. So there are 3 possible ways that we can protect iron from rusting. There is the barrier method, there's galvanizing, and there is sacrificial protection. And we're going to look at each of them. So first of all, the barrier method involves coating the iron with some sort of barrier, and that stops the water or oxygen from reaching it. And the barriers could be as simple as painting, coating it with oil or grease, covering it with plastic, or even covering it with a metal lower on the reactivity series, but we'll come back to this one in a little bit. The most common ways are painting, covering it with oil and grease. As you probably see every day when you're out on the road and you see cars, all cars are built from a steel or an iron body. However, we don't actually just leave that, we put that layer of paint on top of it, and that is one, to make it look nicer, of course, but also it has an actual scientific reason, and that is to stop the formation of rust. If we have the formation of rust on a car, it can cause damage to the structure, and of course we don't want that. Now, galvanizing involves coating the iron with a layer of zinc. Okay, zinc is higher than iron on the reactivity series, and what the zinc does is it again acts as a slight barrier to the oxygen and the water, and it protects it from rusting. If the surface is scratched and the iron is then exposed, the iron still doesn't rust because the zinc is more reactive. That means that the zinc is more likely to react with the oxygen or the water. So the zinc will react with the oxygen or the water before the iron. So because the zinc is more reactive, it is basically taking the place of the iron in terms of the corrosion that's happening. So the iron doesn't rust, but the zinc will corrode. So it's sacrificing itself. And we call this process galvanizing. Galvanizing is an example of sacrificial protection, and it involves attaching the iron to a block of a metal which is higher on the reactivity series. And typically we'll use either aluminium, zinc, or magnesium. And this just means that the more reactive metal is going to corrode before the iron does when the presence of water and oxygen. And this just stops the iron from rusting. So we put the more reactive metal sacrifices itself in order to allow the iron to not rust. And we typically call these blocks sacrificial anodes, and they're used in large structures where any other protection methods would be difficult to use. So if you have a huge structure made of iron or steel, such as a bridge, yes, we can paint a bridge or we can paint a building, but they are very, very large, and sometimes by the time you finish painting, you have to start all over again because you would have your paint chip or being exposing the iron, and that's not particularly useful. So what they might do is they may use these sacrificial anodes instead, and that just allows for a more effective way to stop any rusting. So let's have a look at some past paper questions on this topic. So we're going to start with the June 2012 paper. So the diagram shows a reaction of some metals with cold water and dilute hydrochloric acid. And you can see that we're getting bubbles of gas being formed with specific elements. So we want to use the two diagrams to answer the questions, and we can only use the metals that appear in those diagrams. It's a very important part of the question. So we want to name two metals that are going to react with cold water. So we just look at the picture and we can see that it is calcium and magnesium. And then one metal that reacts with dilute hydrochloric acid but not with cold water. Well, there are two possible options here. We can see that iron reacts with the acid but not water, or zinc is also a perfectly acceptable answer. And now we want to arrange the 5 metals in terms of reactivity. Now, this can be a bit challenging at first, but actually when you break it down, it is quite simple. What you want to do for that is you want to look to see the one that is giving off the most gas. The most gas that is being released, the more reactive it is. Okay, so if we have two that are going to react only with cold water, we know that they must be near the top of the reactivity series. So these ones are going to be at the top, whereas the acid ones are going to be in the middle. So the calcium and the magnesium both react with water, but what one is going to be more reactive? Well, the calcium, because it's giving off more gas. So our most reactive metal is going to be calcium, followed by magnesium, because that also reacts with the cold water. Then we have to go down to the metals with the acid, and we look to see again which one is giving off the most hydrogen. So we've had calcium and we've had magnesium. So now we look at the 3 that are left, and the next in line is zinc, followed by the iron, and then lastly copper, because the copper doesn't actually react at all and it gives off no hydrogen. So there's the mark scheme for those questions, and you can see that we've managed to get them in the correct order. Now this is from the January 2012 paper. So iron is a useful metal, but the one problem with iron is that it can rust. Name the iron compound that is present in rust. Well, that compound is iron 3 oxide, or you can also write the formula, which is Fe2O3. Name the 2 substances that iron reacts with when it rusts. Well, anytime we have rusting, it means that we are in the presence of oxygen and water. And again, you can write the formulas. You could write O2 and H2O. They would also be acceptable. And what type of reaction occurs during the rusting of iron? Well, we are gaining oxygen in this reaction, but we are not burning, so it's not combustion. And what it actually is it is called an oxidation reaction, and that just means the gain of oxygen. Galvanizing is a as a process that can prevent metal from rusting, and in this process the iron is coated with another metal. What metal do we use? Well, for galvanizing in particular, there is only one possible answer, and it is zinc. And then identify one object that is suitable for galvanizing. Well, we want to have it something that is not too big and something that is not too small, and we want it to be something that's going to come into contact with water and air. So a bucket is going to be the most likely thing. And then two other methods that can be used to prevent iron from rusting. Well, we can do any two that we've looked at. So we can have covering it with oil, covering it with grease. We can have painting, using a plastic cover, or even coating with a more reactive metal. Any one of those answers, or any two of those answers, would give you the final mark. And there's your mark scheme. Now that's everything for topic 2D, the reactivity series for single science. Hopefully everything has made sense, but if you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.